Good afternoon and welcome to information retrieval. And let me see, you recall that we are in a section that we're calling decision trees. And we noted a couple of things about decision trees. They are not unique. And we have a goal here. And you'll have to excuse me, I have a cat walking across my keyboard. The goal is to find the minimal depth tree. And unfortunately, there is no algorithm for doing that, but there is this thing called a heuristic, and we described the difference between an algorithm and a heuristic previously. And this heuristic has a name. It's called ID3. It was developed by a statistician. His name was J. Ross Quinlan, an Australian. I think he did this work sometime around 1980. And it's based on this idea of entropy or minimizing entropy. And you may recall last time we considered some population and we said, suppose there are 5 yeses, there are 5 no's, and we pick some attribute A. I know this is review. And on attribute A, we could come down here and we could have 4 yeses and 1 no, and on this value of it, we could have 1 yes and 4 no's. And if we were to take the same population and instead do this on attribute B, and attribute B broke it up this way into 3 yeses and 2 no's, and this was 2 yeses and 3 no's. Okay, first of all, realize what happens when I'm saying here attribute A, attribute B. This attribute A might be something like is tall, and this could be true, and this could be false. Attribute B could be color, this could be red, this could be green. And it's a splitting up of the population into smaller groups. And the last time that we met, we said, well, look at these nodes down here. They're closer. These nodes here are closer to pure, whatever that means. Pure, of course, would mean that we would have either all yeses or we would have all no's. By the way, if we have a node that is pure, suppose we had something like this. Suppose we had 5 yeses and 0 no's, and we're trying to come over here and we're trying to look at what is the entropy of this node over here. Well, that would be h of 5 over 5 comma 0 over 5. And of course the problem you have here is when you calculate the entropy of this, the entropy of 1 is 0, and this is undefined. But in fact, if we had something that looked like this, we would say that the entropy of this node is 0. There's no variability in it. I think you would all agree with that just looking at this. But the point is that the entropy of this node here, we can see is going to be closer to 0 than the entropy of this node here. Now, the way that the ID3 algorithm works is first we look at the entropy in the parent node. So I come over here and we note, and again we mentioned this last time, we have h of 5 over 10 comma 5 over 10. And that of course is equal to h of 1/2, 1/2. And again, we did the calculations previously, that's just 1. So that is the entropy in the parent node. as it should be. It's the same. What we need to do is we need to come down here and look at the entropy in the children's node, but we need some way of talking about what is the total entropy at this level right here. So I'm going to come over here and hopefully I can do some magic. Yes, I can. Just give me a moment here. Okay, so what I want to do is I want to look at these nodes right over here. And when I do that, this node right over here, I guess while I'm writing, let me do it this way. Yeah, that'll work. So the entropy of this node right over here is going to be H of 4/5, 1/5. And the entropy of this node over here is going to be H of 1/5, 4/5. And I come over here and the entropy of this node over here, and I'm referring to this node, that's going to be H of 3/5, 2/5. And the entropy of that over there is going to be H of 2/5, 3/5. Now, like I said, I need some way of encapsulating the total entropy of this entire row here. And I need some way of doing it in this entire row. And what I'm going to do is I'm going to take a weighted average. And by a weighted average, I mean the following. This may not be a particularly interesting example, but we're going to see more interesting ones right here. We notice that over here in this row, okay, off of this attribute, there are a total of 10 instances, and we note that 5 of them are over here, and 5 of them are over here. So I'm going to look at this number, and I'm going to take 5/10 of it, which is of course 1/2, and I'm going to multiply it, and then I'm going to add 5/10 of this one right over here. And this is giving me a weighted average of the entropy in this particular row, which we would say is the entropy, the average entropy over this attribute. I'm going to do the same thing over here. And again, you'll notice that it's just going to be 5/10 this plus 5/10 times that. Well, we should actually go ahead and calculate these numbers. So this H of 4/5, 1/5. And by the way, we notice that this is the same entropy as that. And this is going to happen whenever the thing's split in two like that. Otherwise, it's not going to be as easy. But this is going to be equal to 4/5 log 5/4 plus 1/5 log 5. Okay. Okay, so I want to actually calculate this quantity here, and here is my calculator, and I look at it and I get a little bit worried because I need to calculate logarithms base 2, and I see logarithms base 10 over here, and I see ln, which is a natural log, but nothing base 2, but that's no big deal, okay? We know the following. We know that, let me just get this. I'll put a little box over here, that log of n is just equal to log base 10 of n divided by log base 10 of 2. And I knew that you all knew that, so that's like really cool. So I'm going to come over here and I am going to go, let's see, 5 divided by 4 is 1.25, and I am going to take log base 10 of that, and I'm going to divide that by 2. I'm going to take log base that, and I'm going to say equal. I did that a little too fast. I'm not happy with that. So hang on a second. 1.25, and I'm going to take log base 10 of that, and I'm going to put that into memory. And now what I'm going to do is I'm going to take 2, I'm going to take log base 10 of that, and I want to flip x and y. All right, I hate these calculators. Let's do this again. Okay. Uh, so I know what I'm going to do. I'm going to clear everything. I'm going to come over here and I'm going to take 2 and I'm going to go log base 2 and I'm going to store that into memory. So I'm going to do a memory clear and then a memory plus. Okay, now what I'm going to do is I'm going to go 1.25 and I'm going to go log base that and I'm going to divide it by memory recall, and that is equal to 0.3219. So this is 4/5 times 0.3219 plus 1/5 of, and I'm going to go 5, and I'm going to go log base that, and I'm going to divide it by memory recall, and that's equal to 5 times 2.321. So this is equal to 0.8 times 0.3219, and that's equal to that, plus, and I'm going to go 0.2 times 2.321, and that's equal to 0.72. Okay? And now I'm going to do the same calculation over here. And again, my life is made easy by the fact that I just have to, so over here I did this. Okay, h of 4/5 was equal to that, and this, we'll get back to that in a second. Remember, this number right over here is just the number for h. I'm going to come over here and I'm going to get that h of 3/5 2/5 is equal to 3/5 log 5/3 plus 2/5 log 5/2. Okay, and again, I'm going to come over to the calculator. So 5/3 is 1.667. I'm going to take the log of that. I'm going to divide it by memory recall, and that is equal to 0.7325. So that is 0.7372. And I have to multiply that times 3/5 plus 2/5. And this is 5/2, so that's 2.5. 2.5 divided by memory recall. That's 1.32. So I get 1.32 times 2/5 is 0.4, and that's equal to that. And I go plus 0.7372 times 0.6, and that's equal to 9710. So what's happened here is this is 0.9710. Now remember, all we've done so far is we've calculated the entropies. We have not averaged them. So what we need to do now, we can get our calculator out of the way for a second. I'm going to bring this up here. So the calculator based on these nodes over here, remember that is going to be one half, that 5/10, times 0.7217 plus, and now we have to throw this in there. Well, that's 1/2 of 0.7217. And of course, I've got 2/2 of these. That's just going to be 0.7217. Likewise, over here, what I need to do, I've got to go 5/10, well, that's 1/2 of this entropy here, which is 0.9710, plus 1/2, that's this, of 0.9710. And that's just equal to 0.9710. So what we're saying here is the following. I wish I could combine these screens a little bit better. That if you look at this one over here, the left side, we had an entropy of 0.7217. On the right side, 9710. In other words, the entropy was less on the left than the right. And that certainly corresponds to the idea that this is closer to pure than this one over here. But what we need to do, this is the one last part of the algorithm, is we define this thing called the gain. And we have the gain on a node n, comma, an attribute. Okay, and what the gain on a node n over the attribute is it's equal to the entropy of the node. Okay, and then what we have to do is from that, we have to subtract the weighted, okay, entropy over the attribute. So let's see again what that means going back to our drawings over here. So first of all, what we're trying to do is we're trying to calculate the gain going from here down to here. So the gain would be over the original, the parent attribute, the entropy in there we saw is 1. So what we need to do is we come over here. Remember, we had attribute A and we had attribute B. So what I want to look at is I want to look at the gain of n over attribute A, and that was equal to the entropy in n minus the weighted entropy over attribute A. Well, the original node had 5 yeses and 5 nos. The entropy was 1. So if I come over here, this is equal to 1 minus, and we already calculated that the entropy over attribute A, we calculated was just 0.7217. So that is 0.7217. And what is that equal to? That's approximately, I'll just make it an approximation, it's approximately equal to 28. Okay? Then we had the gain of n over attribute B was equal to 1 minus, and you may recall, you can see it way over here when we calculated that attribute, it was 1 minus 0.9720. So that is approximately equal to 0.03. Okay, so what is the ID3 algorithm? The ID3 algorithm says pick the remaining attribute along that branch, that maximizes gain. So in this case, we saw that the gain was bigger here than here, which would say that we would pick attribute A over attribute B. Now we're going to work through an example, but I'm going to stop the tape for a second.